Hello everyone. In this video, we are going to talk about solids of revolution, and we're going to focus on the disk method and the washer method. So when we talk about a solid of revolution, we're taking some kind of equation. So here's my XY axis, and we are bounding this equation between some we've got some constraints here. So here and here maybe. And we're going to rotate this about an axis. So if we were to rotate this, say, along the x-axis here, it's going to form what's called a solid of revolution because we're revolving this around an axis to create a solid. So if we were to do that in this case, it's going to look let's see if I can and draw this. And you may have to use your imagination a little bit, but it's going to look something like this. So we're going to have this solid in here. It's going to look kind of like a vase. See if I can draw it out to the side. A little bit of curvature here and here. All because we took this equation, whatever this equation was, and revolved about an axis. So we're creating the solid of revolution, and we're asking the question, what um, would be the volume of the solid of revolution? And we've got a couple of ways we can look at this. The first way we're going to look at this will be with something called the disk method. And with the disk method, what we're going to do is we're going to divide this into little disks. So our axis of revolution was here. So I'm going to draw it here. When we divide this in the disk, think about taking a knife and just slicing it into pieces. If we were to slice this into pieces, we're going to get all of these little circles out. It's going to look kind of like just really kind of like CDs, but no hole in the middle of the CD in this case. And what we want to do is we want to find the volume for each of those little CDs. So a little CD is going to have a radius. So we could talk about that radius here. I'll call it R of X. I don't know why it's changing everything in the letters. That's interesting. So I'm going to have that radius here. And we could think about the thickness of each of these little slices. And I'll refer to them as like little CDs. And we're going to add up an infinite number of those. So when we're adding up an infinite number of things, integration is a good way to do that. We know the volume for something that's going to look like this. So this is really, we could think about it like a tiny cylinder is going to be pi r squared h. If we know the radius, and now that radius is going to be in terms of our function here, and our height is going to be in terms of the thickness, it's going to be in terms of depth. So we can use this volume of a cylinder to help us derive an equation for finding the volume for a solid of a revolution if we're adding up an infinite number of these little CDs. Volume of the cylinder is pi r squared h. So the radius is going to be our r squared, and that's going to be in terms of our function, whatever our function is. Or we're going to have to write it in terms of function notation because it's not going to be constant. It's going to change. Like for instance, in this picture, this radius would have a different value than the radius down here. So it's a variable radius in most cases. And our height of our cylinder, you're thinking about these cylinders sideways. So this CD is actually a sideways CD right here. And when I slice this, that height of that cylinder would be our dx in this case. Now notice we're revolving about the x-axis. We're slicing perpendicular to the axis of revolution. That's important. We're perpendicular to the axis of revolution. So here's our formal disk method. if we have a horizontal axis of revolution, like around the x-axis, or we could even go around a different axis, like y equals 3, or y equals -7. But if we're going around a horizontal axis, we're thinking about everything in terms of x, because those slices are going to be perpendicular to that axis, and they're going to all have a height of dx. So volume is pi, and we're integrating from a to b. That radius is squared times dx. If we are revolving about a perpendicular axis of, a vertical axis of revolution, to be perpendicular to that, now we're thinking about that height in terms of y. So everything has to be written in terms of y. So we're thinking about that radius this way. In this example, we want to figure out the volume for the solid of revolution. We are going to revolve f of x equals square root sine of x about the x-axis. So if we were to do that, you can see what's going to come out. It's going to look kind of like a football. We've got to figure out bounds. Now this one, we have a graph. It'd be really easy to see that the bounds are going from 0 to pi. If we wanted to solve that by hand, maybe we don't have a graph later on, we're going to set sine of x equal to 0. So this is where the axis of revolution is equal to the equation. In this case, we would square both sides. And then we're asking where is sine of x equal to 0. That's going to happen at x equals 0 and pi. So we've got our a and b. When I slice this, you can see how everything that's going to come out is going to look like a really thin cylinder, so like a really thin CD, but no hole in the middle. That's important. So it's going to be just like a really small cylinders that are coming out. The thickness is going to be dx. So if you think about that cylinder, that's the height of the cylinder. The radius is going to be from the axis of revolution up to that graph. So to set our equation up, it's going to be equal to pi. We're integrating from 0 to pi because those are our bounds. Our radius is the square root of sine of x. We're squaring that times dx. And then it becomes just a basic integration problem. When I square the square root of sine, I'm going to get sine. When I integrate sine, I get negative cosine. I need to evaluate from 0 to pi. So I'm going to have negative cosine of pi minus negative cosine of 0. Cosine of pi is -1, so negative 1 is a positive 1. Cosine of 0 is 1. So this is going to have a volume of 2 pi. Let's look at another one. We want to find the volume of the solid formed by revolving the region bounded by the graphs f of x equals 2 minus x squared and g of x equals 1 about the line y equals x. Sorry, y equals 1. So let's start by drawing a picture of what this guy looks like. So f of x is 2 minus x squared. So it's the graph x squared, which is a parabola that's up. We're going to reflect it, so now it's upside down, and we're shifting it up 2 units. So now it's going to look something like this: upside down quadratic, shifted up 2 units. And then the graph g of x equals 1. So that's just a horizontal line. So there's our graph. That's what we're revolving, and we're revolving about the line y equals 1, which was actually that part of that bounded region. So notice this region that we're revolving is up against that axis of revolution. Same thing here. It's up against the axis of revolution, which means there's no holes in this. That's why we're not getting CDs with holes in the middle. We're having solid cylinders come out when we revolve. So let's start by figuring out bounds. I need to know where 2 minus x squared is equal to 1. So I'm going to do some fancy math. I'm going to move that x squared over so it's positive. Move the 1 over. So x is going to be plus or minus 1 when I solve that. Volume equals pi. This is going from a to b. Radius squared dx. So we are integrating from -1 to 1. So when I slice this cylinder, so I'm going to rotate it, it's going to look kind of like almost like a ball, if you will. And I'm slicing it perpendicular to the axis of revolution. The height, well, let me refer to it as a radius. That radius is going to be that quadratic minus where that line y equals 1 is. Okay, so that's going to give me that radius value. So how big is the radius for each of these slices? And notice over here, it's going to be different than what it is in the middle. So notice we're going to have a variable radius again. So it's going to be 2 minus x squared minus 1. There's my radius, and I'm going to square it. So let's clean that up. 2 minus x squared minus 1, quantity squared is 1 minus x squared, quantity squared. So how do we integrate that? We are going to expand it. So it's going to be 1 minus 2x squared plus x to the 4th. And then we're going to have x minus 2x cubed over 3 plus x to the 5th over 5, going from -1 to 1. And then I'm going to plug in my bounds. So I'm going to have 1 minus 2/3 plus 1/5. When I plug the 1 in, minus, and then I'm going to plug in the -1. So I'm going to have a -1. That's going to become a positive 2/3 and a minus 1/5. Let's see what we have here. So we're going to have a positive 2 minus 4/3 plus 2/5. I just combined the whole numbers, the thirds, and the fifths together. And then if we were to simplify that, I'm going to cheat. I'm going to do that in my calculator off screen. I'm going to get 16 pi over 15. So there's your disk method. Washer method is similar, only now we're going to have an outer radius and an inner radius. For example, if we were to take this piece of the graph and we were to revolve it about the x-axis here, it's not going to be solid because when I revolve this, I'm going to end up with this piece down here looking like this, and then I'm going to have this big hole in the middle. And you see that hole has a variable radius also. So you can see that right there. The method is the same, still using the fact that we're talking about tiny cylinders and an infinite number of them, which means integration. So we have pi times the integral from a to b, and notice it's going to be the outer radius minus the inner radius here. So you're thinking about the volume of the big cylinder minus the volume of the small cylinder, and if we were to combine that together, that's our washer method. Let's look at an example. We want to find the volume of the solid formed by revolving the region bounded by the graphs y equals square root of x and y equals x squared about the x-axis. So here's our picture of what's going on. So this is x squared right here. This is square root of x. If I want to figure out bounds, I would set those equal to each other. Square root of x equals x squared. I would square both sides. I would move everything to one side so I could factor. And then I would set each factor equal to 0. So x would be equal to 0 and 1. So that's where our bounds are going to come from. And you can see that here, the intersection for those guys would be at 0 and 1. So let's think about outer radius versus inner radius. That outer radius, when I rotate this guy, is going to come from here, which is that square root of x. The inner radius is coming from that x squared. So my setup is going to be volume equals pi, integrate from 0 to 1, the square root of x squared minus x squared dx. And then we're just going to simplify. So when I simplify this, I'm integrating from 0 to 1. This is going to be x minus x to the 4th dx. When I integrate, I'm going to get x squared over 2 minus x to the 5th over 5. When I plug in the 1, I'm going to have 1/2 minus 1/5. When I plug in 0, I'm just going to get 0. And when I simplify, I'm going to get 3 over 10 pi. So that would be the volume of that figure. Let's look at another one. We want to find the volume of the solid formed by revolving the region bounded by the graphs y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. So y equals x squared plus 1 is a quadratic shifted up 1 unit. X equals 1 is this vertical line here. So if I want to look at bounds, so let's look at what's going to happen in this example. We want to find the volume of the solid formed by revolving the region bounded by the graphs y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. So now instead of a horizontal axis of revolution, it is a vertical axis of revolution. So we need to write everything in terms of y. I'm going to make that little note on our notes here. We're going to have to write everything in terms of y. So we've got this quadratic, right? Y equals x squared plus 1 looks like this. And then we've got y equals 1. I'm actually going to draw a clean picture over here. Y equals x squared plus 1 looks like this. X equals 1 looks like this. We know there's an intersection here. The quadratic that's up 1 unit, shifted up 1 unit from the origin, intersects with x equals 1. I could find that intersection point. I know the x coordinate is going to be 1. If I plug 1 in here, the y coordinate is going to be 2. So that's where that 1, 2 point's coming from. Now, notice this one's interesting because at 1, if I were to divide this into 2 pieces, and remember, we are rotating about the y-axis, so it's going to look kind of like a candle, if you will, but part of it's going to be empty up on that top half. So it's going to have a hole in the top half. But that bottom, everything below x equals 1 is going to be a solid piece. So I'm going to divide this into 2 pieces when I form my integration, because I'm using the disk method and the washer method. So from 0 to 1, this piece down here, remember we're integrating in terms of y, is going to be solid. So it's just going to have the function y equals 1, and that's the radius. So remember, I'm squaring it. So now I got to figure out what's happening from 1 to 2. So if I'm thinking about from 1 to 2, I've got to figure out how can I write that radius. This is the washer method because we're going to have a hole in it. So the distance from here to here, which is my bigger radius, is still going to be 1. So that's the outer radius. The inner radius is going to depend on that equation, y equals x squared plus 1, but we have to solve it and write it in terms of y. So let's solve this for x. So it's in terms of y. I'm going to subtract the 1. I'm going to take the square root. And anytime we take the square root, we have a plus and minus. Then we have to ask ourselves, is it the plus or is it the minus? Because we're bounded in the first quadrant by x equals 0 and y equals 0, it's got to be the plus. So it's going to be minus square root of y minus 1 quantity squared dy. And then now we've got something fairly easy we would be able to integrate and solve. Let's look at the next one. And we're really just going to focus on setting this guy up. We have a manufacturer that drills a hole through the center of a metal sphere of radius 5 inches. The hole has a radius of 3 inches. What's the volume of the resulting metal ring? So we could think about a sphere as a circle that's been rotated. If we want it to have a radius of 5, then our equation would be x squared plus y squared is equal to 5 squared. They're rotating this about the x-axis, so we're thinking about everything in terms of x. So here's my picture in 2 dimensions. I'm thinking about this equation as y equals the square root of 25 minus x squared, which would be this guy. And I'm rotating it about the x-axis, which is going to form that ball, that sphere that has a radius of 5 inches. Okay, but we need a hole that has a radius of 3 inches. So if I were to create a line here, y equals 3, and I were to rotate this piece, it would form the figure that I'm looking for. So let's figure out bounds. I'm looking at the square root of 25 minus x squared, which is the top half of that circle. I want to know where that's equal to y equals 3. So I'm looking for these intersection points here. So to solve this, I'm going to square both sides. I'm going to rewrite this. And I'm going to take the square root. And we get plus and minus 4. So this is intersecting at x equals 4 and then at x equals negative 4. So my volume equation is going to be pi. I'm integrating from negative 4 to 4. It's the outer radius squared minus the inner radius squared. That outer radius is that circle. The inner radius is going to be the line y equals 3. And then that's what I'm going to solve. So there's my setup for that. And if you wanted to solve this, I'll do the first step and then I'll tell you what the answer is. Squaring the square root and then squaring the 3 and then simplifying is going to give us the integral from negative 4 to 4 of 16 minus x squared dx. And then don't forget we would multiply by pi to find that volume. So our final answer here would be 256 over 3 pi. That would be our volume.